Last time we started section 1.1, we're looking at a preview of calculus, and we had encountered one of the first sort of full-out descriptive types of things that calculus is able to do when pre-calculus falls short, and that was the tangent line problem. Okay, and we had written down how in calculus what we're really doing is this limiting process of letting these points get sort of infinitely close together. We're still really finding the slope of a secant line if we're using pre-calculus techniques, and we're going to do one of these specifically today. But it's this idea of the values getting really, really close to where they're maybe sort of indiscernible. And so has anybody seen the movie IQ? It's a very cute movie. It's about Albert Einstein's niece, played by Meg Ryan, and Tim Robbins is the mechanic who is like exceptionally bright. And he talks about in this movie about the fact that she asks him to dance, okay? And he's like, he asks her to dance. And she's like, that's not even possible because there's space between us. And even if I cross half the distance of space, every time I get half the distance closer, I'm still never going to get there. And they're talking about a limiting process, right? That's what my points are doing. They're crossing this space and they're never going to actually arrive there if we keep subdividing by a specific value. In this case, in the movie, it was dividing by 2. So let me talk about another one that's an area problem. We actually will get to this in chapter 4. So it's going to be quite some time before we do. And in our area problem, it works like this in terms of calculus versus pre-calculus. So in pre-calc, we can find the area of certain shapes. We talked about that last time. They were very specific shapes, right? Very rigid kind of shapes, so squares and circles and such like that. So circles, maybe rectangles or triangles. And of course, there's a whole list of them. They're more complicated than these, but there's a whole list of them. But most of these most of which are based on the area of a rectangle. For example, you might remember the trapezoid. A trapezoid looks like, let me draw you one for you, looks like this. You've got 2 parallel sides, and then the last one is not parallel to the one across, right? The trapezoid. And I can use an area of a rectangle formula, and I can kind of piece this together, and I can find the area of the trapezoid. Okay, so most of these, not the ones with the circles, but most of the rest of them are based on the area of a rectangle formula. So, and that, whoa, that didn't look like an A at all. Let's try that again. Was length times width, or base times height. That's the area of a rectangle. So what happens in calculus is that we can find the area of arbitrary shapes. But we're still going to be using the area of a rectangle. So let me show you how this works from a picture point of view. So we're going to take an arbitrary shape. It really doesn't matter what you draw. This is what I'm going to draw. And we're going to find this area between a specific point on the x-axis A and another point B. And the area I'm referring to finding is actually if I were to draw a vertical line down to the A and the B. That wasn't great, but let's try it again. Okay, that's as good as it's going to let me do. And if I were to shade all this in, I could find this specific area. Now, I can find it exactly with calculus techniques, but the pre-calculus approach to doing this is another limiting process. What it does is it says, okay, well, let's divide it into two rectangles, or into two areas anyway. And then we can divide it into 4 areas, and then we could go into 8, and then we could keep subdividing. And what we do is we use an area of a rectangle on each of these to approximate. It's not perfect. My picture's not great, but do you see that there's sort of these rectangles, and some of them are a little bit too big and some of them are a little bit too little, right? You know, some of them are a little bit more area, some are a little bit less area than I'm supposed to do. But if I made more and more rectangles, then the heights would be closer and closer. My overages and my underages, that's not a real word, by the way, but the over and the under would be a little bit less each time the more and more rectangles I did. So my number of rectangles becomes infinitely large. Or what you can say is that the width of each rectangle, right, this distance becomes infinitely small. So very much like my points getting infinitely close together, they're really, really, really close, the width of my rectangle gets infinitely small to 0. And it's still based on this area of a rectangle. Okay? Now we're going to do an actual problem with a calculus. One of them is a pre-calc problem. The other one is a calculus problem, but we're going to use pre-calculus techniques to do it. So take a look. We're going to need this graph right here, or this table in a second, because I don't have a way to project my calculator very well in this room. We've got 2 problems. Here's 1 and here's 2. And we're asked in each case to decide if we can use pre-calculus or if we have to use calculus. Write this down. The primary difference is the equation. So take a look. This equation, 4x plus 3, what's that an equation of?
A line.
A line, thank you. The other one, 3x squared plus 2x minus 4.
Fancy curve.
It's some kind of a fancy curve. Yeah, it's a parabola specifically, or a quadratic. But in particular, it's simply not a line. Okay, there's 2 categories. There's line and there's not a line. There is no in between. It's one or the other. If it's a line, like this one, we use pre-calculus. It's easy. Okay, I'll show you how to do it, but it's a pre-calculus topic. So we're going to start out by just identifying that this is pre-calc. And it's because it's a line. So anytime a question is asking you whether you're using calculus or pre-calculus, you need to figure out, are you dealing with a line? If you're dealing with a line, it's pre-calc. Okay? Now, and I guess I could write into the other one, this one's going to be calculus as well. Now, let's actually answer the question that's being asked. It says, consider the equation. So we've got f of x equals 4x plus 3. What is the slope of the curve? Okay, curve is a general description. It doesn't mean it's what we sort of picture in our minds as curvy. Y'all know what I'm talking about, right? I mean, a line's not curvy. It's straight. Agreed? So this is not a curvy curve, but curve is this overarching description. That's why it can be used here. What is the slope of this curve at x equal to 2? There's no calculations necessary. What is the slope of f of x equal 4x plus 3?
4.
It's 4. Right? Yeah, that's an algebra thing that we've learned, right? It's in the location with like y equal mx plus b, m is 4. So what is the slope at x equal 2? Well, actually, the fact that it's x equals 2 is irrelevant. It's got a slope of 4 everywhere, yeah? So the slope is 4. So the pre-calculus questions are ones that we can answer exactly and usually very quickly. Okay? This one, not so simple. It is a parabola. And I'm just going to draw a general sort of shape of a parabola and talk about why it makes it more difficult. Depending on where I am on this parabola, the slope is not the same as every other point. In particular, if I drew a tangent line here or drew a tangent line here, I don't even have the same sign. One has a positive slope and one has a negative slope. I mean, I could even have a zero slope if I drew the line at the very bottom that's touching. It's a zero slope down there. So it matters on this one where I am. Over here, it didn't matter in the slightest, right? Lines are lines. It's the same slope everywhere. So here's how we have to do this. I guess I put my picture on the wrong slide. I'll put the picture over here now. I can do that. Okay, well, that wasn't what I meant to do. Let's try again. Okay, so grab your calculator. We'll start by getting your calculator set up well. I think I should put that a little bit bigger so you can see it better. It's as big as I can do and still be my screen. Okay. In particular, you get to this screen by hitting second table. Okay, does everybody find this screen? Second table? Did it look like that? Okay, it needs to say ask on the first one and auto on the second. Okay. Yeah, so you hit a second. Oh, a second window, I'm sorry. Second window, my bad. Second window is your table set button. Okay, does it say ask and auto on everybody's? Ask on the first one, auto on the second one. You just move the cursor over and just select it. Does all y'all look okay? Mm-hmm. Yeah, everybody good. Okay. What this is doing is it's allowing you inside of the table to input values that you want and you care about them being instead of it arbitrarily choosing X values for you. It's a much easier approach to using your table. We're going to leave our table like this for the remainder of the semester, so you won't have to change it again. Okay, so do you remember when we talked over here on this picture last time? We're trying to get these points to get really close to each other, right? And in particular, on this problem, we're trying to get it really close to the value of x equal to 2, because that's the value they gave us. So what we do is we use values close to 2, a little bit bigger than 2, and close to 2, a little bit smaller than 2. So I've got two tables set up. On the left-hand table, we're going to do values that are smaller than 2. So it's going to be something like 1.9. And then we're going to get closer but still smaller and go 1.99. And then we're going to go 1.999. So first I just want to generate the x values and see that they make sense. Those x values are getting closer and closer to 2, right? But they're all smaller. My right-hand table, I'm going to do the same thing but from the bigger side of 2. So I'm going to do 2.1, 2.01, and 2.001. Again, all close to 2. And getting closer as we go down the table, and all bigger. Okay, does everybody understand why those points are chosen? Okay, let me make one unfortunate comment. Inside of WebAssign, they choose the points for you sometimes, X, and they don't always choose points that are particularly helpful. So fill in the table they ask you to fill in, that's fine, right? But recognize you may have to create a table that's actually going to be helpful on your own, okay? You may not be able to use the table that's been created there to actually give them the interpretation that they're looking for. There's also something to be said for the fact that this is x equal to 2, and if it was something else, like let's say you were approaching x equal to 4/7, just get a decimal approximation for it and do the same thing with the numbers, right? So if it's 4/7, so which is a little bit bigger than 0.5, you're doing values that are just slightly smaller than that, and on the other side you're doing values that are just slightly bigger than that, okay? So it doesn't really matter whether it's a whole value or whether it's a decimal value, you can do the same process. Okay, the next thing that we're going to do, and this one is using your calculator's table. So go to the y equals first, hit y equals, and we're going to put in the equation that we were given. So we're going to put this equation, well, we'll put this expression, say, into y1. So y1 is going to say 3x squared plus 2x minus 4. Once you have that in y equals, I want you to go into your table. So you're going to actually hit, let's see, it is second graph. If there's anything in this picture already, just hit delete on the x values. Just hit delete, delete, delete until they're all gone, okay? You don't need them, delete them out. So you should have a completely blank screen. It should have a column for x and a column for y1. Does anyone's not have the y1 on it? Okay, great. we're going to put these x values in, and you can put all 6 of them in at the same time. That's totally fine. So 1.9, 1.99, and 1.999, and then 2.1, 2.01, and 2.001. Now, on the first one with the 1.9, my screen says 10.63. Does yours say 10.63? Wonderful. So over here, we're going to write down 10.63. Did anybody's not say 10.63?
How did I get away?
Okay. So that's what we did the whole table set thing. We did second window, and we make it say auto ask. You've got them backwards, I think. No, maybe you just haven't deleted them. Maybe you haven't deleted them. Let's try again. You delete them. You didn't delete them. Okay. That's right. We got that taken care of. Okay. Does everybody say 10.63? 10.63? Excellent. So with 1.99, my screen actually says 11.86. Does yours say 11.86? That's not exactly accurate. Okay. So I'd like for you to cursor over on top of the 11.86. And do you see how at the bottom of the screen it gives you a fuller expansion? We're going to write that fuller expansion out to 6 decimals. Now this one's only got 4, but we're going to write 11.8603. You might be thinking to yourself, does the 03 really matter? Well, if we round, we always run the risk of getting an incorrect answer later. And sometimes it will matter. On this one, it probably wouldn't, okay? But sometimes it will. And we're going to do the same thing with the 1.99. If you just go down 1, you'll see that it expands, and it actually expands to the actual full 6 decimals that I mentioned. So we'll write those out, 11.98, 6003. Okay, we can do the same thing for the f of x column with the 2.1s and so forth down. So I'll write down mine and make sure that yours look like mine as well. We'll confirm that we all have the same thing. Okay, so everybody have all those same values? All good? Okay. Now, if we were just trying to find the function value there, and you just look down the f of x column, you'd say that they're both approaching approximately 12. Agreed? Not only that, but because this is a nice, lovely, continuous curve, if you put 2 in, it actually is 12. So do that as your last entry in your table because we're going to need it anyway. If you put in 2, you get 12. Exactly. So this point at x equal to 2 corresponds to a y value of 12. Okay, all good? So somebody tell me what you remember about finding slope. How do we find slope? Thank you. Okay. Some other things that you might remember is you might remember it as rise over run, or change in y over change in x. You could even write it as y1 minus y2 and x1 minus x2, and that would be okay as well. Now, in every problem that we're about to do, this piece right here with the y1 and the x1 is the 212 above. Okay? So all of ours are going to have the form where we're going to take a y value, we'll call it y2, and we're going to subtract 12, and an x value, we'll call it x2, and subtract 2. Every single problem we do, okay? And the x2 and the y2 are going to be the values that we just created in our table. So our first x2, y2 is going to be 1.9 and 10.63. So back in the regular screen in your calculator, be careful with some parentheses depending on your operating system. You might need them, you might not. You're going to put in 10.63 minus 12 over 1.9 minus 2. So for example, in my calculator, because of the way mine shows up, I actually will have to put parentheses around it like this. Newer versions don't necessarily make you do that, but mine does. Okay, now when we write this out for our slope answer, Again, we're going to write it out to 6 decimals for the time being. Okay? What did you get for the slope when your calculator gives you back that calculation?
13.7.
Is it exactly 13.7? Okay, cool. 13.7. Everybody got 13.7? I'm hearing echoes. Wonderful. Okay, let's do the same thing, but now it won't be 10.63 and 1.9. It'll be 11.8603 and 1.99. So I'll write this next one down, and then I'm probably not going to write any more after that because you'll see the pattern. So now I'm doing 11.8603 minus the 12, so I'm still doing minus 12, over 1.99 and still doing minus 2. So this is my first slope, and this is my second slope, M1 and M2. What did we get?
13.97.
Okay, did everybody get 13.97?
13.95.
Ooh.
13.97.
Okay, so let's check the 13.97. Let me see on yours. It's 8603, I think, there, instead of 8605. Okay, this is a really good example. Okay, take the last line you did, and I want you to hit second, enter. What just happened? Did it pull back up the line you just did? And you can go back and you can edit it. So you don't have to type this in every time. You can do second enter to pull it back up, and then make the appropriate changes to get to the next line. Okay, so we have 13.7 for the first one, 13.97. What happens when you use the 11.986003 and the 1.999? 13.997. Agree? Okay, let's go to the next table listing, the ones with the 2 points. So our first one has 13.43 and 2.1 for our denominator. What do you get? 14.3. Okay, how about the second one? 12.1403 and 2.01. Is everybody getting the same things with the 14.3 and the 14.03 on these? Okay, last piece. 12.014003 and then 2.001. What's the last one?
14.003.
Yeah. Okay. All good? Okay, so this is all the work. You don't necessarily need to show this, what I put down in the bottom left-hand corner. I was doing that for y'all benefit, not because I need you to write it down. But the table is the work that you would show for this problem. Okay, that's what you would show if you were doing a quiz question or a test question for me later on, okay? What we're doing in terms of answering the question, though, is we're taking a look at what happens as we go down the table. And the reason I'm saying down the table is because as I move down the table, the x values get close to 2, right? I get closer and closer to x equal to 2 as I move down each of these 2 tables. What value do each of them, because these happen to match, appear to get close to? What value is my slope getting close to? 14, right? It's 14. So each of these are getting close to the same slope value of 14. So up here, we would say that we expect that the slope is 14. And this is the work that supports that approximation or that belief that we have in that value. Understand, we just used pre-calculus, and it was really tedious, wasn't it? It really is. What we just did is really tedious to do this. It works. And in reality, once we get to doing calculus and our calculator actually does things behind the scenes to give us feedback, this is what your calculator does too. It does numerical approaches. It doesn't use calculus. It uses numerical approaches with pre-calc. Any questions on this? Okay, let me make one more, just throwing this out here kind of thing. This first assignment might be your most annoying assignment all semester because of stuff like this, okay? It will get better. Do not think that just because the assignment is short, it's going to take you a short amount of time. It's going to be annoying. It's going to take a little while, okay? So plan for that between now and Wednesday.